All right, we started section 1.2 last time, and the title is talking about finding graphical and numerical limits. And what we talked about was the graphical limit part last time. So we're going to move on into numerical limits. So I mentioned last time as well that when you hear the phrase or the word numerical, it's talking about like actual numerical values, which for us is going to mean a table. We're looking at tabled values. So your calculator is going to be very handy, and we actually set it up last time. If you didn't have your calculator here last time, what you can do real quick here is you can take the button that says window, above window, hit second, and then window, it should say table setup. Second window is table setup. If you did this with me last time, you don't need to do it again, but if you brought your calculator this time, didn't last time, you do. And the first one where it says independent needs to say ask, where it says dependent, it needs to say auto. That's the important thing that you have to have set up in order to do this. So to do a numerical limit, what you're actually doing is you're going to have an equation given, x squared minus 9 over x minus 2, or sorry, x minus 3. And then the value underneath, where it says limit, and underneath it says x arrow 3, means that we want to choose values that approach 3. Okay, so we did something in 1.1 like this. It was for a different purpose, but we did something quite like this, where we used values getting really close to the value of 3 from both sides of 3. So something slightly bigger than 3. And so if you'll remember, the ones that we chose that are really nice progressionally are 3.1, 3.01, and 3.001. And from the other side, I threw my hands in the hair in the wrong direction. The right-hand side for you guys was the bigger values than 3. And then the left-hand side values are slightly smaller than 3. And progressionally, we did 2.9, 2.99, and 2.999. Okay? So if you do have a TI-83, TI-84, or a calculator like a Casio that has tables in it, it's really nice because you can put the y equals, or hit y equals, and you can put this equation in. Now, depending on how your calculator is set up, you might need to put the numerator in parentheses. Like this is the version of the operating system my calculator currently uses. I have a TI-83 that I'm using right here today. Yours might be set up so that it automatically does fractions where it actually looks like it's got a numerator and denominator. If so, then you don't have to worry about the parentheses because it will force it on its own. So x squared minus 9 is in the numerator. X minus 3 is in the denominator. And we're going to go into the table. Yes, ma'am?
Can you remind me how to do that in the calculator? Like where do I put that in?
Y equals. There's a y equals button on the top left-hand corner.
Gotcha.
Hit y equals, and then that equation, either in the form I've written, or it might look like the form that's already on the screen typed in, will go in. And then you're going to hit the table button, which is second graph. And you should have a table show up that has an X column and a Y1 column. And inside of the X column, you can write these X values that we have created, 3.1, 3.01, and 3.001. And if you do, these are the values that should show up. And if they don't, you need to see your calculator so we can fix whatever's going on so you don't make the same mistake again. Now, if you don't have a TI-83, 84 calculator, you're using something else, or you don't have a table feature in whatever you're using, you can just enter these values by hand, right? You can enter 3.1 squared minus 9. You know, press enter and divide that by 3.1 minus 3. You can do that. Yeah.
I did not get that.
Okay.
I don't know what I did wrong.
So you don't put it in here, put them into the table. So you have to go into the table, and there's your values. This is a negative and a minus. So anytime the value is between, you put the minus sign. If you put it at the beginning, it's the negative sign. Okay, anybody else not have the six numbers, the numbers with the sixes?
Mine's giving me fractions.
Okay, let me take a look. Another thing. Is it right now? It's asking you to put in instructions. And later you want the answers in a decimal point. Okay, anyone else's? Okay, if it's all going in correctly with all the sixes showing up, let's do the 2.9 side now. And you should end up with numbers like this, 5.9, 5.99, and 5.999. Okay, everybody's getting the 5.9-ish numbers if you're using a device. Good. So of course, as you go down both these lists, what do they get close to? They get close to the same number, 6. And so when that happens, we would actually say that our limit, actually, let me do it up here. Is 6. Okay? The limit's 6. The next example is quite similar, but what you will actually see is it changed the numerator to have an addition sign, right? So the cool thing is that if that's all that's changed, which it is for us right now, if we hit y equals, we should just be able to change the negative or the subtraction sign on top to an addition sign. And your table's probably still going to already be set up unless you deleted it. So you're still going to have the same 3.1, 3.01, and 3.001, the 2.9, the 2.99, and the 2.999. So all those are it's the same as before. They should still be stored into your table, and you should be getting values now that look quite different, actually. On the second one, it might actually just look like 1806. I wrote that wrong. But if you arrow over and your cursor is on top of it, right, it looks like it's blackened on top of it, the pixelated, it's 0.01. And then the next one is 18,000, 6.001. And on the 2.9s, we have negative 174.1, negative 1794.01, and negative 994.001. Those are the values that show up. If WebAssign wants you to use a specific number of decimals, it will tell you. In fact, it usually does, so that it makes sure that it gets the accuracy, so that it will count it correct or incorrect based on that. So if we go down the first table, the one that had the 3.1, 3.01, and 3.001, what's happening to those y values? They're increasing, like tenfold every time, right? It's almost like you multiplied by 10 or thereabouts to get the next value. And that's going to keep happening, so this is actually going to infinity. It's getting infinitely large. But what's happening on the other side? Yeah, same thing but negative. It's going to negative infinity. So when that happens, we encountered this last time, but from a different point of view, we say that the limit does not exist because the one-sided limits, right, the limit from the right and the limit from the left are not the same. So the limit does not exist. Okay, so that's numerical limits. So both of those types of questions, the graphical limit questions, the numerical type of questions, are going to be inside of WebAssign. The next thing I'm going to show you is something that's not quite done very well inside of WebAssign because there's really not the ability to do so. Any questions before we leave numerical limits? Sorry. Okay, so numerical means all about the tables. All right, so again, hope you have this all written down because I'm not going to wait for you to write it. It's in your notes already. It says, consider the function f of x equals 5x plus 2. That's an equation of a line, right? So line with slope 5, y-intercept 2. If we were to find the limit as x approaches 3 of 5x plus 2, from section 1.3, which I realize we haven't gotten there yet, but we will next time, we would actually be able to very quickly find that the limit's 17 on this particular one, 17. So let's take a look at what the graph looks like, and I'm just going to give you what that is really quick. I know you guys can create it on your own, but we have a y-intercept of 2 and a slope of 5. We'll do it something like that. So it's crossing at 2, and it's going up 5 over 1 each time. So as we come over here to approximately x equal to 3, right here on the graph, the y value is actually the value 17. So if you think about it from a graphical perspective, and I know you just trust me that that's actually true, but your calculator would draw it for you, or you could draw it yourself. If you approach the value that's x equal 3 from the left or from the right, either direction, you get close to a y value of 17. So from a graphical perspective, that makes sense to us. Intuitively, this makes sense to us. It makes everything seem quite reasonable. But the description is actually considered imprecise. So what we're going to do in the last part of this section is recognize that we have the ability, when we have a limit, to do the following. If we get really close to x equals 3, and we have a limit, then we should be getting really close to y equals 17. Okay, and on my picture here, you should all look at that and say, well, yeah, right? Makes sense. There's no jump in the graph. I don't have any disconnects or anything like that. So let's say that we wanted to make sure that the function value and the limit of that function as x approaches 3 are close to one another. So we wanted to make sure that the y value that actually exists there really is the limit there. Perhaps we only want them to differ by 1 unit. We're only 1 away, right? So we're between, 1 away from the 15 and 17 on my limit value. So 16 to 18. If so, how close of an x value is required to ensure that that limit is actually 1 away? So over here, we want my limit to go between 16 and 18 if I'm 1 away. And the question is, how close do I have to be down here to make sure that it's really only 1 away? That's the idea. How close do I need to be on the x values to ensure that? So what we're going to do is we're going to actually find that value specifically for when we are 1 away. So here's my function, 5x plus 2. Here's the y value I'm trying to get close to, 17, right? And I want the distance between those, that's why I'm doing an absolute value, it's the distance between those to be less than 1. Okay, that's going to force it to be between 16 and 18 if it's less than 1. So what we're going to do is we're going to actually take this inequality, absolute value inequality, and we're going to solve. So how do we do that? Well, we're just going to do a little bit of algebra. We have 5x plus 2 minus 17. 2 minus 17 is 15, negative 15, right? If you notice, the 5x and the 15 have something in common, a 5. So we're going to factor a 5 out, and I can factor it completely out of the absolute values because it's positive. If it were negative, I could factor it out as well, and it would become positive, all right? Is everybody good so far? I'm playing with some absolute values. We haven't done that together yet, but then if I divide by 5, what I have is that the x value difference from 3 is less than 1/5. So the number that goes in this blank is 1/5. So I'm going to flip back over real quick to my graph and tell you what that actually tells you. It tells you that in order to be 1 unit away on the y-axis, I can only be 1/5 of a unit away on the x-axis. So mine would have to be between 3 and 1/5 and 2 and 4/5 if I do it as a mixed number. I can only be 1/5 away to ensure that I'm 1 away over here. And that should make sense. Where did that 5th come from? The slope of 5. Right? I mean, that's where it's coming from. It's not a mystery, but that is where it's coming from. I have to be within 1/5. The thing is, though, we kind of chose that I want to be within 1 away kind of in an arbitrary way. How do I decide I want to be 1 away? Well, we just decided, right? We just decided we wanted to be 1 away. So in general, we want to be epsilon away. Not 1 away, but epsilon away. We want to be close, epsilon Greek letter, and for us it's going to be a small value Greek letter. So instead, what you see is that instead of having the 1 over here, we have the exact same inequality we had before, it's just an epsilon. So So everything I did over here that had a 1 on the right-hand side, we're going to do it the exact same way. It's just going to have an epsilon on the right-hand side. So as we work these problems, we're going to take the 5x plus 2 minus 17, right? We're going to combine like terms when we have the ability to do so. We're going to factor things out. And we're going to divide by that coefficient in front. So my x minus 3 absolute value has to be epsilon over 5 away. And again, it's coming from the slope, like we said before. So that's where this thing is coming from. How do I ensure that I get really, really close on the y-axis? Well, I have to be really, really close on the x-axis. How close precisely? Well, there's a ratio. The ratio here is the ratio of 1/5 because my slope was 5. And that's great as long as I'm working with a line that has a constant ratio. Yeah? But if I'm working with a curve that doesn't, things go a little bit differently. So coming into here, we actually have what's called the precise definition of limit. So I'm showing you where it came from by the previous work that we did. But let's say that f is a function defined on an interval containing c. It might actually have a hole at c, and that would be okay. That's what it says, except possibly at c. There could be a hole there. Let L be a real number. If our limit has the limit L, right, the limit of our function is L, then it means that for every epsilon greater than 0, there exists a delta greater than 0, such that if 0 is less than x minus a is less than delta, then f of x minus L is less than epsilon. So let me give you 2 pieces of information right here. Number 1, your homework questions that are on the written homework are going to use this definition. Number 2, the quiz that we're going to do on Friday won't include it. I'm using other questions for the quiz questions because you're getting written feedback on the homework questions that include this material, okay? So at what point do I need to sort of memorize this basic structure of this definition? Exam 1. You're going to have this memorized by exam 1, not by Friday, okay? Let me show you what we're actually using it for in terms of problems, though, because we haven't done anything with the definition yet. We've just sort of developed the idea. Okay, so we're going to start by taking an inequality, much like, or not inequality, a limit, much like we had on the earlier problems, and we're going to find the limit's value. And because we just did it with tables today and we're already set up to do it, we're going to do it with a table, okay? So we're going to set up 2 tables. One table is from the left, one table from the right. My x value here is approaching -2. So I need to have -2.1, -2.01, and -2.001. And then on the other side, I had -1.9, -1.99, and -1.999. My equation in my calculator is 3x plus 2. And then in my table, I'm going to put in these values that are recorded here. And the corresponding outputs that are my calculator is giving me. Look like this. Okay, so is everybody's calculator giving them those values first? Does that look right? So if that's what your calculator is giving you, what can you tell me from a numerical perspective that the limit appears to be? -4, right? So my limit is actually -4. Somehow on my notes I actually had that already typed in up there, so now it's going to appear for us. It's -4. Okay, so that's numerical limit part of it. The part that actually includes what we just did before is writing of the proof. You might not have written a proof for anybody since geometry, I don't know. But the writing of the proof is going to mirror this definition almost verbatim. So it's going to look like this. We know that the limit as x approaches -2 of 3x plus 2 is equal to -4. We know that, and we're going to state why we know that. Because for every, and we'll find this value in a minute, epsilon greater than 0, there exists a delta equal to something. I'm going to fill in what it equals to in a minute. Okay, but the structure is going to look the same from everything I'm writing down is exactly what it'll be every time, just with a different limit equation in there. Delta is equal to something such that when, okay, so we're going to pause right here and we're going to actually do the calculations that I was showing on the previous slide. So we take the 3x plus 2 and we subtract the 4 inside of absolute values. Okay? I'm sorry, subtract -4. My apologies. We subtract the limit value, which our limit value is -4. And we set it less than epsilon. Okay, it's always the function minus the limit values less than epsilon, and we're inside of absolute values on the left-hand side. We do a bit of algebra manipulation on the left. So I have 3x plus 6. 3x plus 6 means I can factor out a 3. And I can divide by 3. So I have x plus 2 is less than epsilon over 3. This is delta. Okay, the conclusion of what we just found, that epsilon over something value typically, is delta. So up here now I can write in epsilon over 3. It won't always be epsilon over 3, it'll be something else. But here's the way the rest of the proof is worded, such that when, so we start at the bottom of the proof and work our way up with our description. When the absolute value of x plus 2 is less than that epsilon over 3, then my function, 3x plus 2 minus a -4, is less than epsilon. So what this is saying is that when I'm close enough to the x value of -2, in fact, when I'm within epsilon over 3 on either side, right on the x-axis, I am guaranteed to be within a y value of epsilon, right? I'm far enough away of epsilon, of the limit value -4 over on the y-axis. That's what this says. Okay, I'm going to not have us do the limit part for this one so that I can show you the written out part, which is the different part for this. The limit for this is actually the number 1. Okay? So let's actually look at what happens on this one because it is different than the last one because the equation is not a line, right? It's not a line. So something different is going to happen, and it's a little bit unusual based on what we just did. So we have our x squared minus 1 is less than epsilon. We can actually write the first part we just said. We know that the limit as x approaches, is it 2? 2 of x squared minus 3 is equal to 1 because for every epsilon greater than 0, there exists delta, I don't know what it is, I'm going to find it in a second, delta such that, okay, all of that I get for free once I know my limit, which I gave you, but you would find it from a numerical point of view. Okay, so I'm sorry, I left one thing out. I left out the limit value. This was minus 3, so sorry, and then minus 1. I apologize. Okay, it's the function value minus the limit. All right, so here's what happens on this one. I have x squared minus 4. Agreed? There is no constant I can factor out of this, right? And last time I could just factor out of 5, or I factored out of 3 in the last example, right? I can't do that here. But x squared minus 4 does factor. So that's what we're going to do next. How does x squared minus 4 factor? Okay, x minus 2, x plus 2. So at this point, one of those factors is going to be the one that we need right here. Okay, one of them will. The other one won't. I'll tell you what to do about that one. But one of them is going to be the one we need. And we can determine it based upon what x value we're approaching. Because it's always going to be x minus that value. So it's always going to be, in this case, x minus the 2 that I'm approaching, which means the one that I don't want to go away is this one. It needs to be part of the inequality when I get to the very end. But that x plus 2 piece, I do need that to go away. Okay, I need it to turn into some kind of a number. Okay, I can't just divide it to the other side because then I've got epsilon varying based upon a variable x. I need it to be based on a constant number. So what do? Well, what we actually do, and this is the part that's a little bit weird, is that we let our x value be close to, I'll pause there, be close to the value 2. That's what we want. We want our x value to be close to the value of 2. So we're going to say that our x value is going to be, let x be between 1 and 3. Okay, if you're between 1 and 3, are you close to 2? I mean, we could argue about it a little bit, but you're pretty close to 2, correct? Okay, and what you're going to do is you're going to pick the larger number of that pair. So for us, that's going to be, we're going to pick a 3. Okay. I'll show you why the number 3 is preferable in a second, but we're going to pick 3. So let x be between 0 to 3. And then what we do is we actually plug that in for this x value. So we don't mess with the other one. We want that one to stay, x minus 2. And over here, we're going to evaluate this with a 3 in there. 3 plus 2 is less than epsilon. Obviously, that gives us a 5. And when we divide, we have x minus 2 less than epsilon over 5. So why did I pick 3? Why didn't I pick 4.5? Or why didn't I even pick 1? Because it's in that interval. Well, the reason that I picked 3 is because it's the maximum. And when I have the maximum value in here and I divide by it, I make something smaller. So I've taken the interval and I've made it even tighter. I want my interval to be as tight as I know for sure that I need, right? And so that's why I've done that. I've made my interval tighter. So over here, as we're finishing this up, that epsilon now is equal, that delta is equal to epsilon over 5. And we can finish our proof. So such that, I left out a word, the word was when x minus 2 is less than epsilon, then the absolute value of x squared minus 1, minus 3 minus 1. I want to leave that 3 out apparently today. Minus 3 minus 1 is less than epsilon. That first one should have said epsilon over 5. Okay. So as you're doing your homework right now for this initially, you have the same structure. Every proof that you write down is going to mimic mine perfectly. You've got it all there. It's straightforward. When we get to the test, you need to memorize the language structure of this proof. That's just it. You've all been asked to memorize something at some point in your life before. You can memorize this too, okay? Write it on a note card, have somebody quiz you. But you'll be memorizing that when we get to exam 1, not by Friday. Any questions? Yes?
Okay, so when you said we need to keep x minus 2, how do you know that's the one you need to keep?
Because my x value is approaching 2. And it's always this value that we're trying to get it close to. So x minus 2 gives me the difference how far away I am from the value of 2. So they always match. So like over here, this x minus, whoa, that wasn't what I meant to do. I meant to click on that one. This is x minus 2. So over here I have x plus 2 because x minus negative 2 is x plus 2. So it always comes from the underneath part of what the limit is I'm having x approach.
Okay. So it'll be the opposite sign of
It will.
what the actual.
Yeah, it'll always
okay.
be the opposite sign. Yeah, right. All right, we will stop there for today.